one-shot deviation principle is true for finite extensive form game with perfect information. Okay? So then the natural question is, what if the game is not finite? Right? And also, what if there is no perfect information? So the natural question is whether one-shot deviation principle continues to hold true even for these other cases, right? So the answer is, not surprisingly, sometimes one-shot deviation. Okay, so let's focus on infinite games. Then for some infinite games, one-shot deviation principle is held true. But for some other infinite games, one-shot deviation principle does not apply. Okay? So if you ask one-shot deviation principle for infinite game, then my answer is it depends on. Okay? So that's the reason I specifically mention here that one-shot deviation is only applied to, and is in this statement, extensive form game. So I can make exactly same comment, remark for games with imperfect information as well. One-shot deviation principle holds true for some games with imperfect information, but does not hold for some others. Okay? But one thing good to keep in your mind is, even though one-shot deviation is not generally true for infinite games and games with imperfect information, it is actually true for all games, all infinite games, and all games with imperfect information, which I'm gonna discuss this semester in this course. Okay? So even though one-shot deviation is not generally true for for games other than extensive form game with perfect information, finite game with perfect information, even if it is not generally true, it is still applicable for all games, which you can see in my slides and my problem set, and also my exams and any games you will see throughout the semester. Okay? So which means that whenever you try to solve a game, even if it is infinite games, at least in this course, you can safely say that we can use one-shot deviation principle. And same for the games with imperfect information. All games you will see in this course, even if it is game with imperfect information, still you can safely use the one-shot deviation principle. Okay? But it's good to keep in your mind that one-shot deviation principle is not generally applicable to all games. That's simply not true. Okay? So that's one quick comment I'd like to make before we move on. Okay, so in the next 1 hour of the lecture today, I'm gonna discuss one potential, actually important application of soft-game perfect equilibrium. So namely the application to bargaining problems. Okay, so this is kind of the way that we use the theory of soft-game perfect equilibrium to solve some economic problem. Okay, so we're going to apply these things to bargaining problems as an example of application. Okay, so first of all, I uploaded this lecture slide on the Canvas, but at the same time, I also uploaded another document on the Canvas in the folder titled by supplementary notes. Okay, so on the Canvas, if you open the supplementary notes folder, then there is another note, literally supplementary note, which is you can see on the screen. So this is one lecture note I used, a part of lecture note I used last year. Okay, So this is just literally supplementary notes. I mean, it includes additional information you might want to know about application of game theory, application of game theory to bargaining problems. Okay, so if you learn more, you can just download this thing and read by yourself. And of course, if you have any question, during reading this thing note, then you can also ask me. Okay, but the lecture will be mostly focused on the slide here. Okay, bargaining. So I don't really feel like I have to argue why bargaining is important in economics. I mean, I think all of you, all economists and all students kind of can agree that bargaining is really important to some in economic theory. Economics, okay, so it covers a lot of things, but one of the most important thing in economics is to understand how a price is determined, right? So, and bargaining is definitely one way to answer that question. Namely, I can answer that, but basically prices are determined, not always, but in many cases, determined by the negotiation between a buyer and a seller. Okay? So I'm gonna call that problem as bargaining problem. So bargaining problem means that the problem of how to understand bargaining between two parties. For example, buyer and a seller. Okay? So if you study that problem, then hopefully you can understand how a price is determined. Okay? However, bargaining is not really restricted only to price negotiations, right? I mean, bargaining can be observed in all other places as well. Like, if you look at politics, then there is also political bargaining between politicians, right? I mean, two parties can negotiate, bargain about, which bills they will, pass or not. Okay, so political bargaining is just perfect example of bargaining. Another example of bargaining. So in this case, by studying political bargaining, we are seeking for understanding of political process instead of determination of prices, right? But still, that political bargaining can be also analyzed exactly the same way. And also, bargaining is also observed in, for example, as another example, for example, in every houses, in every family. Okay, so me myself, I always negotiate, bargain with my wife to determine which stuff to purchase and how to use my wage, my income, etc. So clearly there is some bargaining stuff there, right? I mean, I like to increase my happiness, and my wife also her own objective, right? So we have to bargain with each other to determine how to use our income together. So the bargaining theory is which bargaining theory we're gonna study can be also applied to that kind of problem as well. Okay. Okay, so let's. There is a lot of different kinds of bargaining theory in literature, in economic and game theory literature. But obviously, I don't have really time to study all of them. So I'm gonna focus on very simplest things, simplest form of bargaining theory. Among all available things you can find out in the literature. Okay, so let me begin with the simplest thing, simplest bargaining game first. So this is actually what we already have seen before. So Jamaican bargaining game. So there are two players. Let's say player one seller and player two buyer. So buyer and seller, they are negotiating to determine what is the price of the good that the seller is trying to sell. Okay? And let's say that the buyer's value of the good is 1, and which means that if the buyer purchased the good at price P, then the buyer's payoff is 1 minus P. Okay, 1 minus price. And there's no value, the seller has no value to the good, so basically the seller's payoff is simply equal to the payment from the buyer. So which means that if they trade at price P, that the seller's final payoff is equal to P. Okay? And if they fail to trade, then both of them get 0 payoff. Okay? So this is just exactly the game we actually already studied last week and also this week. Okay, so we already argued that this game has unique subgame property equilibrium such that player 1 chooses S1 equal to 1 and player 2 chooses yes for any possible offers of player 1. Okay? So indeed, given that player 2 will always say yes, given that player 1 knows that player 2 will say yes all the time, then it is clearly the best response of player 1 to choose S1 equal to 1. Okay? So, and it is also easy to check that player 2 saying yes is Nash equilibrium for all the subgames. Okay, so in terms of bargaining theory, this outcome is pretty striking or interesting because basically the theory says that the seller gets the entire surplus. Okay? So in other words, okay, so let's say, remember that the seller has no value the seller attach no value to the good, and the buyer attaches the value equals to 1. So there is potential surplus from trading equal to 1, right? And they have to determine price, but actually you can say that the process of choosing price or process of determining price is actually equivalent to the process of, you can equivalently say that they have a cake or pie of size equal to 1, and they have to decide how to divide it, right? So that is alternative way to describe the whole process. I mean, choice of price or determination of price is equivalent to the determination or choice of shares of the pie equal to 1 in the problem of dividing a cake or pie. Okay? So in this lecture I'm gonna sometimes I will describe everything in terms of the problem between buyer and a seller, but sometimes I also describe everything in terms of the problem of dividing a cake or pie between two players. But obviously two things are exactly equivalent with each other in terms of mathematics and all the important mathematical structures. Okay, so this outcome is kind of striking or interesting because it says that basically player 1 who makes a proposal actually enjoys the entire surplus or entire share, entire cake or pie. Okay? Okay, so actually the reason that player 1 can enjoy entire pie is actually, basically in this case, player 1 has all the bargaining power, right? I mean, player 1 makes an offer, S1, choose S1, then player 2 only can accept or reject it. So in that sense, player 1 has all the bargaining power here. Okay, so and player 1 make use of that bargaining power, and as a result, the player 1 can enjoy the entire pie, entire surplus, leaving 0 for player 2. Okay, so then let's make this problem a little bit more interesting. So in the previous example, if player 2 says no, then that's the end of the game. That's the end. There is no more things that player 2 can do, right? I mean, player 2 gets 0 payoff and go back home. That's it, right? But let's say that let's make this process game a little bit more interesting by adding one more stage. One more stage that follows the buyers saying no. Okay? So let's say more specifically, let's say that if the buyer says no, so so buyer says no, that means no agreement is reached. If buyer says no, then there is no agreement. Then in previous case, both of them get 0, and then that's the end of the game. But now, alternatively, let's say that instead of 0, each player obtains WI as a final payoff for each player. So W1 for player 1 and W2 for player 2. Okay? So then so this is the game tree for that case. So player 1 again chooses S1, an offer for player 2. Then player 2 can say yes or no. If player 2 says yes, then the outcome is exactly identical as before. But now let's say if player 2 chooses no, then player 1 gets payoff equal to W1 and payoff equal to W2 for player 2. Okay? So, for example, you can understand this game. For example, okay, so this is the game that player 1 and player 2 have to play if two parties can seek to resolve dispute or bargaining situation through arbitration if they fail to reach an agreement. Okay? So remember that here we are looking at the case where player 1 and player 2, they have to divide a surplus equal to 1. And if they fail to reach any agreement, then they can go to, for example, court and then let the court decide, who gets what. Okay? So in that case, is basically the court, so there is some arbitration process, by the court if they fail to reach any agreement. And you can understand, of course, court outcome is kind of uncertain, right? I mean, no one really can say whether they win the legal process for sure or not. So court process is, arbitration process is uncertain, but player 1 and player 2, they can always calculate a expected payoff, right? I mean, considering what is the probability of winning and what is the outcome, payoff, conditional on winning and conditional on losing, etc. And you can just understand W1 is the player 1's calculation of his or her own expected payoff from the arbitration process. And W2 is also player 2's arbitration process. I mean, expected payoff from the arbitration process. Okay? So naturally, we can assume that W and W2 is less than 1. Why? Remember that because there is a pie size of 1 that they have to divide, right? Then at the end of the day, after the arbitration process, again, they will anyway have to divide it, right? But so which means that W1 and W2, the sum of W and W2 is never larger than 1, right? So moreover, if you think about some legal fee or cost, any kind of cost they have to pay during the arbitration process, naturally it is natural assumption that W1 and W2, the sum of two numbers is less than 1. Okay? So I'm gonna keep that assumption. W1 plus W2 is less than 1. Okay, so then let's ask what is the effect of this arbitration process? What is the effect of this arbitration process on the equilibrium outcome? Okay, so that is essentially asking to solve this game. Okay, so we can solve this game again with backward induction. So again, there are infinitely many subgames after any S1. Okay, but the buyer's decision problem is actually quite simple still. So remember that if player 2 chooses yes, then player 2's payoff is 1 minus S1. But if player 2 chooses no, and then her or his payoff is W2. So which means that, for example, first of all, as long as 1 minus S1 is strictly larger than W2, then player 2 has to choose Y. Case 1, if S1, so remember that S1 is player 1's choice, and if S1 is smaller than 1 minus W2, so this is equivalent to saying that 1 minus S1 is larger than W. So this payoff is the payoff from saying yes, right, for player 2. And this is the payoff from choosing N, choosing no for player 2. So if this is strictly larger than this, then player 2 has to choose Y. Okay? So player 2 has to choose Y for any subgame in any subgame such that S1 is strictly less than 1 minus W2. Okay? Any question? Okay, so case 2, what if inequality holds in the opposite direction? So if S1 is strictly larger than 1 minus W2, so that is true if and only if 1 minus S1 is strictly less than W2, then again this is the payoff from choosing Y, and this is payoff from choosing N. Right? So this is payoff from arbitration process, and this is the payoff from accepting and making a deal with the seller. So in this case, player 2 obviously prefer to go for the arbitration process. So in this case, player 2 chooses N. Okay, then the remaining case is such that S1 is exactly equal to 1 minus W2. In that case, player 2 is actually indifferent between two actions, Y and N. Okay? Okay, so as did for the ultimatum bargaining game without arbitration process, let's draw payoff of player 1 for each cases. So we have U1 payoff of player 1 on the vertical axis, and S1 the choice of player 1 on the horizontal axis. Okay, so we have some threshold there. S1 is equal to 1 minus W2. And if S1 is smaller than 1 minus W2, then player 2 will say yes. And then which means that player 1's payoff will be equal to S1. Okay? So on this part of the graph, the player 1's payoff looks like this. So this is the straight line with 45 degrees. Okay, then what happens if S1 is strictly larger than 1 minus W2? So I'm asking what happens in this case in terms of player 1's payoff. So player 2 will choose no, right? So player 1's payoff will be equal to W1. Right? So if S1 is larger than this number, then player 2 will choose no, and so which means that they are going for the arbitration process, and the payoff from that process for player 1 is W1. Okay, so that was our assumption here. Okay, then, okay, by the way, so here we have 45-degree line. So the value of U1 here is 1 minus W2, right? And remember that we assume W1 plus W2 is less than 1, right? So which means that W1 is less than 1 minus W2. So I just move this term to the other side, then W1 is strictly less than W2. So which means that the payoff here is W1, and that is strictly less than 1 minus W2. Okay? So that's what happens if S1 is strictly less than the threshold, 1 minus W2, and S1 is strictly larger than the threshold. Okay? And what about the remaining case? What if S1 is exactly equal to 1 minus W2? So we just discussed that, player 2 is indifferent, right? So any action or any randomization between Y and no, so that will be best response for player 2. Okay? But however, exactly by the exactly same argument for the ultimatum bargaining game, there we, actually saw that even if player 2 is indifferent between yes and no, when S1 is equal to 1, we argued that in equilibrium, player 2 has to choose Y. Right? Yes. Because otherwise, then player 1 has no best response. So clearly, there is no equilibrium. So something, that kind of equilibrium does not exist. Let me be precise. If player 2 randomize when S1 is equal to 1, then we saw that for the ultimatum bargaining game without arbitration process, there is no such a equilibrium. Okay? So using exactly same logic, same argument, here you can say that even if player 2 is indifferent in this case, player 2 has to choose yes. If player 2 randomize in this case, then player 1's payoff from choosing S1 equal to this number is somewhere between two numbers, right? So in that case, you can see player 1 has no best response. Obviously this part is never be a best response, and any number, any S1 over this range is also not a best response, because, for example, this is not a best response because you can improve your payoff by increasing S1 a little bit. And actually, you can continue to do the same thing, all the time, right? So in that case, clearly player 1 has no best response. So in order to make sure that player 1 has best response, which have to be the case in equilibrium, player 2 has to say yes when S1 is exactly equal to 1 minus 1. Okay? So basically, we just repeat exactly same argument again to solve this case. The same argument we used for the case without arbitration. Okay? Any question? Yeah. So the last one. Okay, so it is clear. So this graph is clear to you, right? I mean, this part and this part. this the line. We have two lines. I mean, it's okay. I mean, we have two lines. Which this one or this one? Both. Okay. So here S1 is less than. So we are drawing the picture of player 1's graph or player 1's payoff for each choice of S1. Okay. So player 1 first choose S1. Okay. And then player 2 will choose some response, right, to that S1. So, and player 1 can calculate his or her expected payoff based on the expected response, right? So, for example, let's say player 1 chooses S1, then let's say player 1 expects that player 2 will say yes. Then player 1's payoff will be S1, right? Because he knows that S1 will be accepted. Okay? So we are doing that exercise here. So let's see the case that S1 is less than this threshold, 1 minus W2. Okay? So that refers to the first case here. Right? In the first case, we are discussing the situation such that S1 is strictly less than 1 minus W2. Right? So if S1 is strictly less than 1 minus W2, so this inequality is equal to this inequality. So remember here, okay, so notice here that this is the payoff of player 2 if player 2 accepts, right? And this is the payoff of player 2 if player 2 rejects. So this is strictly larger than this one, which means that player 1 can expect if I choose S1 strictly less than 1 minus W2, player 2 will accept, so my payoff will be S1. Right? So the player 1 here is the seller, and in our analogy, player 1 is seller and S1 is price, and the seller's final payoff from trading is just equal to the price. Okay? So which means that as long as S1 is less than this point, payoff is equals to, so over this range, player 1's payoff is equal to S1. Okay? So, and the graph of this graph, this equation is, so here we have variable on the vertical axis, and here we have variable on the horizontal axis. So this graph is the straight line with 45 or 45. Okay? So, and then what about this case? If S1 is strictly larger than 1 minus W2, so that falls to the second case here. So actually the situation is exactly opposite for the player 2. Player 2 will get higher payoff if player 2 says no. Right? So player 1 has to be able to anticipate that outcome, right? Whenever player 1 chooses S1 larger than 1 minus W2. And in that case, if player 2 chooses no, then player 1's final payoff will be equal to W1. Right? I mean, because if they fail to reach any agreement, then they go for the arbitration process, and player 1's payoff from that process is W1. That was our assumption. Okay? And this W1 actually has to be smaller than this number, which is 1 minus W2, because of our assumption that there is some loss during the arbitration process. For example, some legal fee or whatever it is. Okay? And what about the case where S1 is exactly equal to 1 minus W2? Then, okay, and if player 2 chooses no, for sure, then payoff for player 1 will be equal to W1 in this case, right? And if player 2 says yes, for sure, the payoff will equal to 1 minus W2. Okay? And however, here we just observed that player 2 is actually indifferent, right? So player 2 can actually choose any randomization between Y and no. Anything can be best response for player 2 for that case. For example, if player 2 randomizes yes and no with equal probability, then payoff will be just between in the middle of two extreme cases. Okay? Now, yeah, okay. Then the next thing is, which is really crucial, is, okay, so even though player 2 is indifferent between yes and no, if S1 is equal to the threshold, in equilibrium, player 2 has to choose yes, for sure. Why? Because if player 2 chooses, if player 2 does not choose y with probability 1, then the graph, this point will be somewhere in the middle of between 2 points. So in that case, player 1 has no best response. This graph has no maximum. Okay? So, and that means, if player 1 has no best response, then that is not a subgame property equilibrium. Because in subgame property equilibrium, everyone have to choose best response in any subgame. But if player 1 has no best response, then there is no way to choose best response, right? I mean, trivially, obviously. So player 1 has to have best response, which means that actually player 2 has to choose y with probability 1 in equilibrium. So this is exactly the same logic we used when we conclude that ultimatum bargaining game with no arbitration has a unique subgame property, even though player 2 is indifferent after S1 being chosen as equal to 1. Okay? Any other question? Okay, so then there is unique, our conclusion is there is again unique subgame property equilibrium such that, so here what I really mean here is, okay, so I didn't really explain what I mean by this. So this inverse means that player 1's sigma 1 S1, this, so this symbol, I'm sorry, let me begin with this. This symbol means this node here, initial node. Okay? So here what I mean by here, by this graph is that I'm gonna call this, I'm gonna refer or call this node with this symbol. Okay? So I don't know how to read this symbol, but you can see, you can. So this is kind of a label of this node. Okay? And this mathematical notation here is, okay, so it means that the probability that player 1 chooses S1 equal to this thing, 1 minus W2, at this node is 1. Okay? So this mathematical equation simply means that in equilibrium, player 1 chooses S1 equal to 1 minus W2 with probability 1. Okay? And so these things, the math things in the second line, you can understand that in a similar way. So this is strategy of player 2. So S1 is this node, the node following player 1's choosing S1. So here S1 can be any number between 0 and 1. So this means that if player 1 chooses S1, where S1 can be any number, then probability of choosing Y, probability of player 2 choosing Y is equal to 1. Okay? Is it clear? Is my notation clear to everyone? Okay, so this this means that everything here on the screen means that there is unique subgame property equilibrium, and in that unique subgame property equilibrium, player 1 chooses S1 equal to 1 minus W2 with probability 1. And player 2 chooses yes with probability 1 whenever S1, player 1's offer is between 0 and 1 minus W2. And with probability 1. But for player 2 will choose and with probability 1 whenever S1 is strictly larger than 1 minus W2. Okay? Just some mathematical notation I'm going to use. But basically, in English, it means that there is unique subgame property equilibrium, and in that unique subgame property equilibrium, player 1 chooses S1 equal to 1 minus W2 with probability 1. Okay, so there is no randomization of player 1. And then player 2 will choose yes if S1 is larger than or equal to 1 minus W2. And player 2 chooses no if S1 is strictly larger than 1 minus W2. Okay? This is kind of, my notation I'm going to use all the time. Here, there is vertical line here. So on the right of this vertical line, I'm going to put the name of each node. Okay? And on the left of this vertical line, I'm going to put one possible action that a player can choose at that node. Okay? And sigma I of that thing is the probability of choosing that action at that node. Okay? So, personally, I prefer, this mathematical notation is easier to write down and read and understand. Because, alternatively, you can say, just describe everything, in English, but it can be very long and lengthy. But if you write down everything with mathematical notation, it's very simple to write and understand. So personally, I prefer that way to describe equilibrium strategy. But if you prefer using English, writing down everything in English, that's perfectly okay. As long as you write down everything precisely. Okay? Okay, so then what's happening here is, okay, let me repeat one more time. Player 2 strategy is, I'm going to say yes as long as your offer is less than this threshold. But I'm going to say no if your offer price is larger than this threshold. Okay? So that is player 2 strategy. And then player 1, given that strategy of player 2, player 1 will choose S1 equal to 1 minus W2. And player 2 will choose yes. Okay? Okay, so then what is the message of this game? Okay, so basically, let's think about what is equilibrium payoff. Final payoff in equilibrium. So player 1's equilibrium payoff at the end of the day is S1, which is equal to 1 minus W2. Okay? So at the end of the day, player 1 gets payoff equal to 1 minus W2. Okay? And player 2's equilibrium payoff at the end of the day is equal to W2. Okay? So player 2's final payoff is exactly equal to her respective payoff from going for the arbitration process. Okay, so you can alternatively interpret this game slightly different way. So you can think of W2 as an outside option of the player 2. Right? Outside option, what I mean by outside option is the payoff that player 2 can get if they fail to reach any agreement. Okay? So for example, it can be anything, you can pull outside option. But anyway, so it's the value of outside option is equal to W2. So in this particular context, the outcome outside of player 2 is going for the arbitration process. Right? And that equilibrium analysis tells us that player 1 allows player 2 to enjoy exactly equal to the payoff exactly equal to outside option. Okay? And then player 1 enjoys the the remainder of the pie after subtract the outside option, the portion equal to the outside option of player 2. Okay? So that is really common strategy, right? In the real world as well. Let's say you are a buyer and the other guy is a seller, and let's say you have an outside option, which is, for example, you have some opportunity to purchase exactly same good at price equal to, let's say, $10, right? So buyer has outside option, which is equal to 1 minus 10. I'm sorry, 10 is too large number. So anyway, so let's say buyer has outside option, which is the opportunity to purchase exactly same good at price equal to 10 from another seller, right? Then what is the best strategy that the seller can use? Just offer exactly equal to that outside option, right? So that is really common strategy in the real world as well. And players choose payoff is increasing in W2, so that also has some some implication, right? I mean, let's say you don't really have any bargaining power. You are player 2 in this game. Then still there is some way to improve your payoff. I mean, you can get some good outside option, then you can improve your payoff, right? So that's also really what is really commonly observed in the real world, in any kinds of bargaining. So this example highlights kind of importance of outside option. Okay. Okay. So we have discussed, analyzed two bargaining games, ultimatum bargaining game and ultimatum game with arbitration. Okay, so in both cases, basically the player 1 will enjoy entire pie except for except for player 1 basically allow player 2 to enjoy payoff equal to the outside option, and player 1 enjoys the remainder. In the ultimatum bargaining game, player 2's outside option is 0, so player 1 enjoys the entire pie. In the second game, player 2's outside option is equal to W2, so player 2's equilibrium strategy, equilibrium payoff is actually equal to W2, and player 1 enjoys the residual of the pie. Okay? Okay, so far so good. I mean, these two games are kind of good, nice games, but it has some limitation if you think about what's really happening in the real world. If you compare two games with the bargaining process you can observe in the real world, both games have very crucial limitation. So here we assume that player 2 never can make a counter offer. Okay? So if player 1 makes an offer, and player 1 can make an offer, and if player 2 reject, and that's it. That ends the game without any agreement. But if you think about the real world bargaining process, typically the other player also can make some counter offer. Okay? So in remaining, for remaining 20 minutes, I'm gonna try to extend our bargaining game, including adding some possibility of player 2's making counter offer. So let me begin with the simplest game, such that player 2 can make some counter offer. So now game has two periods, period 1 and period 2. So in the period 1, player 1 makes an offer, which is equal to S1, and player 2 can accept or reject. If player 2 accept, then they make a deal. Okay, so player 1's payoff will be 1 minus S1. I'm sorry, player 1's payoff will be S1, and player 2's payoff will be 1 minus S1. Okay, so far it is exactly identical to what happened in our first ultimatum bargaining game. But things begin to be different if player 2 chooses no in the first period. If player 2 chooses no in the first period, then the game moves on to proceed to the second period, and in the second period, it is now player 2's turn to make an offer. Okay, and player 2 can make an offer. Basically, propose how to divide the cake, and then player 1 can say yes or no. If player 1 says yes in the second period, then they make a deal and they trade. Okay, so then the payoff is as we described before. And if player 1 says no, then the game ends now. So there is no more period after period 2. So then that's and yeah, that's the end of the game if player 1 says no. Okay, so two things. First of all, for now, let's say there are several things. Okay, so I'm gonna use this notation. SI always means player 1's share proposed by player I. Okay, so if S1 equal to 1/2, if I say S1 is 1/2, that means player 1 proposed that I'm gonna have half of the cake. Okay? And if I say S2 is 1/3, then the subscript 2 means it is proposal made by player 2, but S2 itself represents the player 1's share, made according to that proposal. So which means that if S2 is equal to 1/3, that means player 2 proposes that player 1 will get 1/3 of the cake, and player 2 will enjoys the residual, which is 2/3. Okay, so just piece of notation agreement between you and me. Okay, SI always means player 1's share according to player I's proposal. Okay, so that's one thing I would like to emphasize. And the other thing is that I'm going to assume that there is some discounting for the future payoffs. What is discounting? I believe all of you took the course in macroeconomics last semester. And I believe there was a lot of discussion about time discounting. Okay, in economists, typically we assume that people discount whatever happens in the future. Okay, so $1 today and $1 in the next year, they value differently. Okay, $1 today is more valuable than $1 in the next year. Okay, so there can be many reasons, right? I mean, for example, if you save $1 today to the bank, then there is typically some interest. So you will enjoy actually more than $1 in the next year. So that's the reason why $1 today and $1 in the future they value differently. Okay, and so I'm gonna use that idea again. I'm gonna incorporate that idea as well. So two period happens, period 1 happens first and then period 2 happens later. So which means that any payoff realized in the second period has to be discounted. So I'm going to use discounting factor delta. So which means that, for example, if player 1 accepts S2 in period 2, so remember that S2 is player 1's share proposed by player 2. So if player 1 accepts this S2, then player 2 will enjoy S2 out of the entire pie, but that payoff is discounted in the perspective in the first period, the viewpoint in the first period. So in the first period, player 1 will think that if I will accept S2 in period 2, then my payoff is delta minus S2. So future payoff is discounted. And player 2's payoff will be, for the same case, in terms of period 1's point of view, payoff of player 2 will be delta minus S2. Delta times 1 minus S2. Okay? Okay, so much discussion so far, but everything we discussed so far can be summarized with this game tree. So again, it is player 1 who moves first. So first player 1 chooses S1, right? So S1 is player 1's proposal. So S1 means it represents the amount of share that player 1 would like to have. Okay? And if player 2 chooses yes, then that's it. Player 1 will enjoy S1 and player 2 will enjoy the residual, the remainder, the remaining part of the pi k. So her payoff will be 1 minus s1. So that is the case when player 2 chooses yes in the first period. Okay? And in the second, but however, if player 2 chooses no, then they will basically the same game, another ultimatum bargaining game, except that now player 2 makes an offer and player 1 chooses either yes or no. Okay? And there is one more difference. I mean, the payoffs are discounted if they reach an agreement in the second period. Okay, so we would like to solve this game. We would like to solve what is subgame perfect equilibrium for this game. Okay, then again backward induction. We want to use the backward induction. But we are not going to really go to the end of the game. But we first look at what happens if player 2 says no in the first period. Let's say player 2 says no in the first period. Then player 1 and player 2 has to play a ultimatum bargaining game with arbitration, right? And we have to have, if we have any equilibrium, then that equilibrium has to be also subgame perfect equilibrium for that subgame, right? So I'm talking about, okay, so let me repeat one more time. Okay, so let's say, so we are gonna use backward induction to solve this game. So at the end of the day, in the very last moment, player 1 has to choose some action, but that is pretty trivial, right? We already know that player 1 will choose yes. If my offer is, the other player's offer is less than or bigger than some threshold. I mean, this is kind of simple. And then we have to look the next subgame, which is, you can see on the screen here, the lower part of the screen. Okay, so and if we have any equilibrium, then that equilibrium also has to be equilibrium for that subgame as well. Right? So that's the idea of subgame perfect equilibrium. Subgame perfect equilibrium means that equilibrium strategy is Nash equilibrium for any subgames, right? So which means that subgame perfect equilibrium strategy, if you restrict that strategy into this subgame, then it has to be also subgame perfect equilibrium for that smaller subgame. Okay? To put another way, okay. Okay. So, however, we already know what happens if they play subgame perfect equilibrium. We already know what happens. Right? So, going back to this slide, here we show that if player 1 and player 2, if they play ultimatum bargaining game with arbitration process, then basically there is two players, right? Proposer and responder. Responder payoff is equal to her outside option, and proposer will be the residual of the pi, right? So here the outside option of player 2 is W2, so responder's outside option is W2, so responder will enjoy W2 of the K, and proposer will enjoy 1 minus W2. Okay? And moreover, we show that that is unique subgame perfect equilibrium for this game. Okay? So we're going to use that fact to solve the game with 2 periods. Okay, so if player 1 chooses no, if player 2 chooses no in the first period, then they move on to the second period. And in the second period, they play a subgame. But that subgame is exactly equivalent to the ultimatum bargaining game with arbitration. Okay? And we know what happens there. The responder's share of the cake will be equal to his or her outside option. And proposer will get the residual of the pie. Okay? So here, of course, we have role of player 1 and player 2 switch, right? It is player 2 who makes some offer in the second period, and player 1 will respond. But it does not really matter, right? I mean, what is really important is whether the guy is whether he or she is responder or proposer. Okay? So anyway, so we already know exactly what happens in this game. So here player 2 is proposer and player 1 is responder, right? And responder's outside option is equal to delta times W1. Okay? So which means that in this sub-game, the only equilibrium outcome is player 2 will allow player 1 to enjoy the pie share of the pie equal to W1, and player 2 will enjoy the residual of the pie. Okay, so you can ignore delta for now because that is simply discounting factor. Okay, so anyway, so in terms of physical description of what happens there, player 2 will offer 1 minus W1 for player 1. I'm sorry. Player 2 will offer W1 for player 1, then player 1 will accept it. So at the end of the day, player 1 will enjoy the pie share of the pie equal to W1, and player 2 will enjoy 1 minus W. Okay? It can be a little bit complicated. If you have any question, I mean, you can simply ask me to repeat one more time if you think you could not really follow. Let me briefly repeat what I have done here. Okay, very briefly. So if player 2 says no in the first period, then they have to play ultimatum bargaining game with arbitration process, right? And we already know what is the only unique equilibrium outcome for that sub-game, right? So based on our observation here, so this is our second game we discussed today. We know that in that sub-game, responders will enjoy equal to outside option, and proposer will enjoy 1 minus responder's outside option. That is the only equilibrium outcome if they play ultimatum bargaining game with arbitration process. Okay? And if you look at this case, this sub-game here, this is exactly the ultimatum bargaining game with arbitration process. Okay? Except that now the responder is player 1 and proposer is player 2. Okay? Because it is player 2 who makes an offer in the second period. But anyway, we already know that there is unique equilibrium outcome for that sub-game for the second period. And in that unique equilibrium outcome, responder will enjoy the size of pi equal to outside option, which is W1, right? Player 1 is responder. And player 2, who is proposer, will enjoy 1 minus responder's outside option, which is 1 minus W. Okay? So whenever player 2 says no, both players understand that the outcome in the second period is always player 1 enjoying W1, player 2 enjoying 1 minus W. Okay? That's what have to happen in the second period. Okay, then actually that observation makes our analysis really simple. Okay, so actually you can simplify this game tree into this form. Okay, so what happens here? If player 1, let's say player 1 chooses S1, which can be any number between 0 and 1, okay? So that's what happens in the first period. Player 1 makes an offer. Then if player 2 says yes, then player 1's payoff is S1 and player 2's payoff is 1 minus S1. If player 2 says no, then they have to play the game in the second period. But we already know that in that game, in that sub-game, player 1 will enjoy W1. So if player 2 says no, then at the end of everything, player 1's payoff will be W1, but there is discounting. So we have to multiply delta. And player 2 will enjoy 1 minus W1 of the pi, but also there is discounting for player 2, so we have to multiply there. Okay? So we can summarize whatever happens in the second period with these two numbers. So this is the payoff of player 1, whatever happens in the future, and this is payoff of player 2 from whatever happens in the future. Okay? So we are doing backward induction. We already know what happens in the second period if they reach to the second period. And using that information, we incorporate that information to this game tree. Okay? Any question? Okay, so then what is this? This is just another ultimatum bargaining game with the arbitration process. If you know, I mean, of course, story is a little bit different, but anyway, so there is some payoff that player 1 and player 2 can enjoy if they fail to reach an agreement, right? So you can, so the delta W1, that is the payoff, and if player 2 chooses payoff for player 1, if player 2 chooses no, and this is payoff for player 2 if player 2 chooses no. Okay? So here the story is a little bit different, but mathematically this is just another kinds of ultimatum bargaining game with arbitration process. Mathematically speaking. Okay? So this game is mathematically exactly equivalent to this game, right? After we make some modification for the payoffs for the case that player 2 says no. Okay? Questions? Okay, then again we know how to solve this game, right? So in this case, we know that responder will enjoy, at the end of the day, responder will enjoy payoff, responder's payoff will be exactly equal to the outside option. And that outside option is this number, delta minus 1 minus W1. And proposer, which is player 1, will enjoy 1 minus the responder's outside option. So this game has unique sub-game perfect equilibrium such that in the first period, player 1 offers S1 equal to this number you can see here on the screen, 1 minus delta minus 1 minus W1. So in the second term here is the player 2's outside option for the case that player 2 says no in the first place, in the first period. So player 1 offers this number, and then player 2 will say yes. Okay? Any question? Okay, so maybe this numbers, the exactly form of equation there can be difficult to understand because calculation can be messy. But idea is very simple, right? So we are just doing backward induction. If they if they reach to the second period, then whatever happens in the second period is just another ultimatum bargaining game. Okay? And we know what happens in the second period. We know what happens in the ultimatum bargaining game. So we know what will happen if player 2 says no. Okay? And calculation can be messy, but in principle you can calculate payoff for player 1 and payoff for player 2 for the gain in the second period. Right? and I just write down that payoff here. No, this is payoff for player 1 if player 2 says no in the first period, and this is player 2's payoff if player 2 says no. If you get that card, that point, then what happens in the first period is also another version of ultimatum bargaining game. Okay? So, and we know what happens in that ultimatum bargaining game. Okay? So that's the idea of backward induction. You first analyze what happens in the last period, and given that you can simplify what happens in the second last period, etc. Okay. So I mean, yeah, again, calculation can be messy. So actually, it can be not easy to get exact answer here, 1 minus delta times 1 minus W1. But I think the idea of the entire process has to be clear too. Okay. So you can check, if my calculation is correct or not, after the lecture by yourself. Okay, so let me make one more comment. Okay, so now we have two periods bargaining model, but maybe you can ask more, right? I mean, this model is probably better than the ultimatum bargaining game in the sense that player 2 can make a counter offer, right? But maybe you can ask, okay, so still we have the same problem. In the second period, if player 1 says no, then the game ends, right? But it's kind of strange, why player 1 has to leave after saying no in the second period. Maybe player 1 can make another offer, right? So that makes our bargaining game 3 period, right? In the first period, player 1 makes an offer, and in the second period, player 2 makes an offer, and in the third period, player 1 makes an offer again. Okay? But in that case, okay, so now we have 3 periods, so situation is even more complicated, but still we can apply the same idea. You can first ask what happens if they reach to the third period. So what happens in the third period is just one version of ultimatum bargaining game, and we know what happens there. And then that makes whatever happens in the second period also another version of ultimatum bargaining game, right? And that makes whatever happens in the first period, that makes whatever happens in the first period another version of ultimatum bargaining game. Okay? So in principle, you can calculate what equilibrium play has to be. So what is common? And you can add more period. You can make a 4-period bargaining game, 5-period bargaining game, etc. But again, the game is, as the game becomes longer and longer, your calculation, the amount of work you have to do becomes a lot, bigger and bigger all the time. But still, the idea is again the same. You apply the backward induction to solve the bargaining problem. Okay, and for all cases, as long as number of period is finite, then anticipating what happens in the future, both players make an agreement in the first period immediately. Okay? Because at the end of the day, just they have to play ultimatum bargaining game in the first period. Some game equivalent to the ultimatum bargaining game in the first period, and we know that in that ultimatum bargaining game, player 1 and player 2, they always make a deal. Okay? So that's basically what I tried to write down here. So I mean, you can continue to make the bargaining process even more complicated, allowing any kinds of finite periods in the game with alternating offer between player 1 and player 2. And this proposition says that for any t, so capital T refers to the stands for the number of periods. Okay? So you can, if you think of t period alternating offer bargaining game, then for any capital T, there is only one subgame perfect equilibrium. And in that unique subgame property equilibrium, two players make a following agreement in the first video. So, and these numbers can be calculated with backward remote. Okay? So, and then the next question is, what if t is infinite? I mean, any finite number capital T can be unsatisfactory, right? So maybe, we have to answer what if T is infinite, which means that they have to, in alternating order, they offer until they finally reach an agreement. Okay, so that's what I'm gonna talk about next week. Okay, so I'm gonna also discuss a little bit more about T period alternating over bargaining game. Okay, but but I want you to try to calculate all these numbers by yourself. Okay, applying the same idea of backward reduction. Okay, so I want you to check whether my calculation here is correct or not. Then, and so that's what it's not really a problem set, but kind of exercise you can do by yourself. And then next week I'm gonna finish bargaining problem, with by discussing what happens in capital TC. Okay? Okay, so if you have any questions, otherwise that's it. See you next week.